Hello, my name is Drew Langford, and I am a junior studying physics at the University of Notre Dame. Today, I'll be talking about the AERO-VISTA interactive spectrogram display. This project was completed in the summer of 2020 during a virtual REU with MIT Haystack Observatory. Before I begin, I want to thank my research advisors for their support and guidance throughout this project. A brief summary of my talk includes a background on the AERO-VISTA mission, to provide some of the motivation on why the AVIS display is needed. I'll then move into a high-level description on how the software is organized, and finally wrap up the talk with a demonstration of the software, showing how some of the dynamic features are going to be implemented and how it can assist in mission operations. The AERO-VISTA mission is led by scientists and engineers at MIT Haystack Observatory. The mission was manifested to launch in last fall through NASA's CubeSat launch initiative. When the mission launches in 2022, the CubeSats will be placed into a high-inclination orbit to study the auroral regions of the Earth in the radio frequency. To go along with the exciting science, there are many first technology demonstrations also involved with this mission. For one, in order to study the auroral regions in the radio frequency, AERO and VISTA were both equipped with MIT Lincoln Laboratory's novel vector sensor. This sensor is capable of collecting each component of the electromagnetic field, telling scientists much more about the radiation sources that they are studying. Further, AERO and VISTA will be completing the first attempt at in-space interferometry. Interferometry is a popular ground-based radio astronomy technique used. However, moving this technique into the space environment opens up a lot of exciting opportunities for future radio science as a whole. To give a good idea of the daily operations for the AERO-VISTA mission, I'll be going and detailing some of the processes in this graphic. So to start at the top here with the AERO and VISTA satellites, here they're depicted doing an interferometric observation of the aurora. In particular, they'll be about 20 to 100 kilometers apart in this configuration, orbiting about 500 kilometers above the surface of the Earth. During these types of observations, they'll actually be collecting about a terabyte of data a day. And this is far too much data to be downlinking over the few ground passes that we'll have. So instead of the entire data being downlinked, summary files will be downlinked to ground stations at Moorhead State University. These files will then be run through data processing pipelines at MIT Haystack, and they'll be available to be inspected by the global science team using the AVIS display, which is the subject of this talk. So the AVIS display is going to allow the science team to identify events as well as select further data processing on board the spacecraft. And those commands will be sent and uplinked through the Haystack, Moorhead, and near-Earth network dishes back to the AERO and VISTA satellites, where the in-flight processing can take place and the cycle can be completed. The need for the AVIS display, as you saw in the previous graphic, arises out of a data rate problem between the ground stations and the spacecraft. So as a reminder, the AERO and VISTA will both be accumulating about a terabyte of data each day, while our ground passes will only be able to downlink on the order of gigabytes. This means that mission operations requires a tool to most efficiently utilize in-flight processing. Therefore, the AVIS display is going to accomplish this challenge in three ways. One, it'll provide spectrogram plots for a large number of summary data files to be downlinked from the spacecraft. Therefore, it won't just be one experiment at a time that the scientists can view. It will be an entire collection of events that will help and aid in the event identification. To go along with that, the dynamic spectrogram display will allow the scientists to correctly identify through enhancing their views of the summary data. And finally, the display having an interactive selection tool will most easily integrate into in-flight processing decisions for uplink to the spacecraft. So before we hop into some of the software organization, I just wanted to quickly overview some of the scientific objectives that the science team is hoping to learn more about during the AERO-VISTA mission. The first one is the auroral kilometric radiation. The AKR is the most powerfully naturally occurring radiation in Earth's atmosphere. It's caused by the plasma physics phenomenon known as cyclotron maser instability. However, for poorly understood reasons, there's higher detection at the ground level than what is theoretically expected. Another phenomenon known as medium frequency burst is a broadband left polarized emissions that is created at the onset of polar substorms. And the generation and duration of medium frequency bursts in the ionosphere is completely unknown. So these are two really fascinating aspects of our atmosphere and the ionosphere that the science team is really interested in learning more about during the AERO-VISTA mission. On the left here, you can see a picture of a past spectrogram, radio frequency spectrogram, which shows an example of a medium frequency burst during one of those polar substorms. And on the right is a nice image taken from the cupola of the International Space Station orbiting over an aurora around 400 kilometers, which is a similar altitude that the AERO and VISTA spacecraft will be orbiting when they're taking their own measurements of the aurora here in a couple years. This graphic gives the overall structure of the AVIS software. The AVIS software both contains front-end and back-end code. The back-end portion of the software is contained in the MetaViewer package. This package contains 4 modules: the MetaTime, MetaReader, util.py, and SpecMeta modules. The summary data will begin as a digital metadata formatted file, which is from the digital RF package, a package maintained by a research scientist here at MIT Haystack. Once the information is extracted using the MetaReader and MetaTime.py files, the data will then be further formatted using the SpecMeta.py file and turn into interactive functions using the util.py. These interactive functions are actually plotly-objects, which then, along with the assets folder, work together in the app.py module to create the dashboard running on a server, either local or remote. The front end of the AVIS display has 4 different sections, allowing for the scientists to interact with the data and make informed decisions on event selection and in-flight processing. The display controls allow the scientists to dictate what experiment they're looking at in addition to what frequency bands they're interested in. Further, the user can select the time units as well as channel that is being displayed. The metadata info gives a quick snapshot of the data file that's being displayed. This includes the sample length as well as sample rate of the sample data. The display bar along the top allows for the spectrogram to be a dynamic user interface. For example, the scientist can change the scaling, the color map, as well as the X, Y, and Z limits being displayed on the spectrogram. Finally, the bottom encompasses a number of different selection tools for the scientists to make informed decisions on the events that they want to be further processed on board the spacecraft. Okay, so now we'll be going into the demonstration portion of the talk. So all is needed to start up the AVIS display is just to be located in the in the directory where the AVIS software is held. Just in a terminal running the Python file app.py. We'll then start the server. It's running local on my machine right now. So copy and pasting the link and then putting it into any web browser will pull up the AVIS display. So in this demonstration, I'm kind of going to be working through the process that a scientist would be as if they were trying to make selections and decide on events to uplink to the spacecraft. So how the data will be formatted is actually in different experiments. So in this case, we have simulated data from the AERO and VISTA spacecraft. We'll take a look at the AERO data. We can also decide what time units and channels we want to be looking at. So the channels represent the different aspects of the vector sensor collecting each component of the electric and magnetic field. So the loops are the magnetic field, while the dipole and monopoles are the electric field. We can look at both loops individually as well as combined together. So for example, we can look at loop B here, and we'll see a different spectrogram than just the dipole A. However, we can also combine them all together in a total and get the full intensity of the electromagnetic radiation that the vector sensor was seeing. The metadata info just gives us a quick snapshot, as mentioned before, of the file. So this was a 110-second sample length, and our sampling rate is right around our ideal sampling rate, 10 Hertz. All right, so getting into the actual spectrogram figure, we have the frequency on the y-axis. So currently we're in the science band, so it goes from about 0.5 to 5 megahertz. As well, the x-axis is the time. So here we have about a 10-second span of the entire sample length. We can also dynamically change what the spectrogram looks like. So for example, there's different data scaling options. You can scale the y-axis, color map, as well as a plot format if you want just to save the spectrogram output. We see that there's some intensity here around 2.3 megahertz, but if we want to kind of select out some of the that intensity to look at more contrast, we can increase the Z limits. This will then kind of select out that high intensity portion, and we can study that further. If we want to make a selection, there are a couple options on how to do that. You can make a lasso select or a box select. What you're actually doing is selecting a number of points which are scattered throughout the spectrogram. And so you can show those points, your different selection options, by clicking the Show Resolution toggle down below. So here we can see the selection points are pretty sparse. And if we want a better frequency resolution, we can up that to about 5 bins per each megahertz. Okay, so now that our frequency bins are appropriate, we can then go and take the box select tool and select out a number of these points. And we can see that the bounds are printed in the selection bounds table down below. Once we're happy with the selection, we can go into the event types to label it. So in this case, we can label it unknown, as well as designate the processing type that we would want on this. So we'll go with sparse frequency here. Then to save the selection, clicking this button will then populate the table down below. And there are also, you can make multiple selections. So going back to a lower Z limit here, we can see a number of different higher intensity regions. So we can save this selection as well. Go down here, save another selection, one more, maybe the length of the observation, changing the event type. We think this is a roar, and we want to do fast processing type. So all of these are going to populate, and you can look at the entire sample length too, to get a good idea on what type of processing you want on board the spacecraft, as in this is just the sample data that we're looking at. To actually export this data, it's fairly easy. You can create a custom file name, or it will just have its pre-designated file name, which is the experiment that the data is from, as well as the number of selection files attached to that file name as many selection files that have been made. Exporting this as a YAML file will create a file in the selections folder, which is located in the AVIS software. And that can be used and pulled from to do further in-flight processing after it's been uplinked to the spacecraft. So as you saw in the demonstration of the AVIS display, the software is capable of tackling at least a portion of this data management issue which comes up during mission operations. In future development, we hope to incorporate a telemetry data display to allow the scientists to view the region of the Earth that the data was taken from, We also are looking for a more efficient memory usage, as in the sample lengths will be lasting multiple minutes long, and incorporating that into the entire length of a sample into one spectrogram is quite memory intensive. And finally, we want to be able to look at simultaneous spectrograms at once. So, for example, AERO and VISTA will both be taking their own data sets, and viewing both spacecraft's data sets at once would be really advantageous for determining the types of events and data processing that is needed. Thank you for listening to my talk. I hope to see you at the live question and answer session on Tuesday, April 27th at 2 p.m. Eastern Time, 11 a.m. Pacific Time. I'd be happy to answer any questions about the AVIS display, Dash Plotly, or the AERO-VISTA mission as a whole. Thanks, I hope to see you there.